Oh, it's 8:22. So I had a little thought, and I had a little bit of a understanding. Then I totally turned it on its head. Ugh. So I'm looking at the 3-flip Möbius strip cut down the middle, turned into a frame knot, then a knot. And I'm looking at the Jones polynomial, the knots that I get from transforming a 3-flip Möbius strip into frame knots and knots. That didn't make any sense at all. 3-flip Möbius strip, you can see it's intact, but when you cut it down the middle, there it's got 3 flips, 8 twists, and 1 edge. When you cut it down the middle, when you add an edge, you add an extra boundary. So there, it has 8 twists, 2 edges, 2 boundaries, and there's a trefoil knot amongst it. And then you can organize that into like this little thing here that's a coil, and that knot is actually right here. And that knot has a Jones polynomial with this function. And I've inadvertently found that when I was doing my book, so I realized that the knots were chiral. There's right-handed and left-handed versions. So here's some of the knots. You can see the Jones polynomial. That's the function. Minus 4, minus 3, minus 1, minus 4, minus 3, minus 1, minus 4, minus 3, minus 1. So these are all, what chiral are they? Look, so here is clockwise, which is minus 4, minus 3, minus 1. And then counterclockwise goes, here's the function here, it's opposite, right? It's plus 3, plus 1, plus 3, minus 4, I think. Now, so basically, there's only one function for all these knots because they have all the same etiology. But I made a 5-flip Möbius strip and turned it into a frame knot, and lo and behold, it has the same Jones polynomial. You can see it's v to the t minus t to the minus 4 plus t minus 3 plus t to the minus 1. That knot there has 9 crossings. Look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, 10 crossings because, well, I don't need to explain why it has 10 crossings. I think I know why. And there's also this other manifold. You can picture a manifold of a propeller with 3 blades, and you put 2 of them face to face, and before you connect the tips of the blades, you add a half twist in the same direction to each. So that goes to make an interesting manifold that can only be described as kind of like, it'd be like 3 strips of paper connected like this, and each strip has a half twist in the same direction. Well, that has 1 edge, and this is it here. I don't know what the manifold is called, but then this is a normal Möbius strip. This is the counterclockwise and clockwise, and they all have the same Jones polynomial. But these knots are not the same because they have a different etiology. That comes from that funny manifold I described. And I'm using Warwick University's Jones polynomial calculator. I'm not doing it by hand. I did that once or twice, but that's a chore. So you can see all the knots that I found. And I got to look more closely at the Jones polynomial because ultimately what I'm interested in is finding a way to count how many knots there are. The open question for me is, how many knots with 6 crossings does a 3-flip Möbius strip when it's cut down the middle and given 6 crosses to make a frame graph, and that frame graph is transferred and made into a knot diagram? How many knots are there? I found about 80, but I don't know if I found them all because I don't have a way of checking my results. So this is my knot book. This one here is an anomaly. That's a mistake. That does not exist. That has a Jones polynomial equal to 1, which means the unknot, and I know that I opened that curve and put it back together. I was studying the trefoil knots topology. So if anyone is familiar with the Jones polynomial and they can get some of these knots or look at some of these knots or make some of these knots and they want to add to this, then by all means please do a video reply, or I took them apart with Whitney tricks. That was an idea of mine too. And some of them make the unknot. So these, the trefoil and the alternating figure 8 knots, make the unknot. But this group here, which is called the braid group, it doesn't make the unknot. It leaves behind 4 loops. And the 4 loops represent the 8 twists that are left in the manifold. I'm putting the Möbius book away now.